Hello everyone. The topic of this presentation is card shuffling. Me and my teammates Pallavi, Singh and Raghav are going to be discussing about different card shuffling mechanisms such as the top and shuffle and the rifle shuffle and how many shuffles are optimum to achieve randomness in a deck of cards. The first approach in card shuffling is the top-in approach. Under the top-in approach, we have a set of cards. We just take the topmost card and plug it into different positions randomly in the remaining cards. For example, if we have a deck size of 3 cards and we take the topmost card, we can either place it in the second position or in the middle of the other remaining 2 cards. So the possible permutations are 1 2 3, 2 1 3, and 2 3 1, whereas the probability of achieving 1 3 2, 3 2 1, and 3 1 2 is 0, as we are just playing with the topmost card and we would never get the reverse order. The next shuffle we are discussing is the rifle shuffle, which is a very popular shuffling technique used in casinos all over the world. In rifle shuffle, if we have a deck of n cards, we cut the deck into 2 packets. So the first packet would contain the k cards, whereas the other packet would contain the remaining n minus k cards, and we try to interleave the cards so that we achieve a perfect shuffle. For example, if we have a deck of 3 cards and we cut the deck in the topmost positions or in the last positions, the order of interleaving wouldn't change at all. But if we cut the deck in the middle, in the second position or the third positions, we would get 3 possible combinations of the interleaving. So the probabilities of each of this would be 1 by 8 for the topmost card, and if we're cutting in the middle, it would be 3 by 8. If we try to calculate the probability of ordering, it would come up to be 1 by 2 in case of ordering, whereas if we use permutations instead of ordering, the probability of having 1, 2, 3 would be the highest, which is 1 by 2, as we get that order in 4 possible cases, whereas the probability of each other interleaving would be 1 by 8. We need to learn about permutations so that we can calculate mathematically how random our shuffle is. So, the arrangement of a 5 deck card by moving the first card to the end of the end of the deck, which is happening in top and shuffle, would be 2 3 4 5 1. Whereas in case of a perfect rifle shuffle, in which each card from each deck would alternate each other, would be 1 5 2 6 3 7 and 4 8. If pi3 is the complete reversal of the 5 card deck, it would be given by 5 4 3 2 1. So a convolution of pi1 with pi3 would simply reverse the order of pi1 as well, as pi1 was initially given by the permutation 2 3 4 5 1. The new result after convolution would be given by 1 5 4 3 2.
Let us analyze the concept of convolution. So it's nothing but the mathematical representation of multiple shuffles or repeated shuffling. It is given by the formula in the slide, which says Q1 and Q2 is the summation of multiple shuffles. So it's not just repeated shuffling, but it's also a mathematical representation of 2 different shuffles. What is rising sequence? So rising sequence of a permutation is a maximal consecutively increasing subsequence. So for cards, let's assume a deck in some order labeled in increasing order and perform a chosen permutation on them. So we're considering an example. So we have a deck labeled 1, 2, 3, 4, 5, 6, 7, 8. We permute it with the permutation. So the deck now is in the order 4, 5, 1, 6, 2, 3, 7, 8. We start with the card, say 3, and look for 4 after it, but we don't find it. However, we find 2 and then 1 below it. So 1, 2, 3 is one rising sequence. Then suppose we start with 6. We then get the rising sequence 4, 5, 6, 7, 8, and that exhausts the cards. So the permutation has exactly 2 rising sequences. So it's easily seen that the result of one rifle shuffle must be a permutation with 2 rising sequences, or the identity with 1 rising sequence. So how do magicians use this property of rifle shuffling in card predictions? First, they do a single rifle shuffle and ask us to pick a card and put it back. So this creates a disturbance in the rising sequence, causing a single turn. Hence, the card can be predicted. So now the question arises is, how far away are we from randomness? When we ask how many times we need to shuffle, we're not asking how far to go in order to achieve randomness, but rather to get close to randomness. This is where we come to the topic variation distance, which is the difference between two probability distributions. So we have Q1 and Q2 on Sn. So Q1 is the density calculated for rifle shuffling, and Q2 is for complete reversal. The density that gives probability 1 for 3 to 1 and 0 for all other permutations. So we can see in the table that for Q1 it's half until 231 and 0 for 3 to 1, whereas for Q2 it's just 1 for 3 to 1 and the rest it's 0. So here Q1 minus Q2 gives us the output as 1 and the densities are as far apart as possible. So for variation distance, the lesser the variation distance means that the card is shuffled properly.
The biggest problem with the convolution is that it just takes only the perfect number of shuffles, and it's the probabilities and the randoms is not counted in it. So that gives us an opportunity to bring in the property of Markov chain and its properties inside to analyze how a shuffle behaves. So let us analyze the rifle shuffle using a three-card deck of using the Markov transition matrix, which brings in the probabilities of each stage and the next possible stage. According to the Markov chain and its property, it is memoryless, which means that it is just dependent only on the previous state and not any other state. The future state is just dependent on the previous state and not any other state. So the given matrix is the transition matrix for a three-card deck of using rifle shuffles. As you can see, there are only 8 possible combinations. That's why we're able to put it in this page. If we go for 8-card deck, it would be 128 possible combinations, and it wouldn't fit in this one page. So let us see where we achieve the actual randomness using the Markov chain properties. When we just multiply the P matrix by multiple times, we could see that the probabilities of achieving each state goes to around 0.16 to zero point 0.7 at seventh multiplication, which means at 7 shuffles we can achieve a proper randomness where the possibility of achieving each state is 0.16 to zero point 0.17. This means we need at least 7 shuffles to get the randomness, and if you increase more than 7 shuffles, maybe 8, maybe 9, the amount of probabilities of each state doesn't vary that much. It stays close to 0.16. So we can say that p equals 7 means that it has achieved a stability. The given graph indicates the amount of randomness which is created by the shuffles and the number of shuffles which was taken. So we can see that there is a sharp drop when the number of shuffles crosses 5 and it ends at 7. So after 7, then the actual randomness it kinds of stabilizes. So we need at least 7 shuffles to get a proper randomness in major cases, but 7 is not ideal to get the actual randomness. So it tends to go to infinity. So we can say that 7 shuffles is the least number which we need to get the ideal randomness. And so if you're going to a casino anytime, please ask for 7 shuffles if you're using a rifle shuffler, or else you could just walk away. Thank you.